Today we'll start with concavity, and we can determine concavity using multiple methods such as the first derivative test and the second derivative test. Now, what is concavity? If we look back over here, we can see that this is a concave down function, because the concave, if we take it as a parabola, it will be like a parabola facing down. So it is concave facing downwards. This is concave down. Same way, this is like a parabola facing upwards. This is concave up. You can determine the concavity using the first derivative test or the second derivative test. The first derivative test states that if a differential function y is f of x has the first derivative increasing in an open interval I, it will be concave up. If f dash of x is decreasing in the open interval I, it is concave down. Using the second derivative test, we say if a differential function y is f of x is twice differentiable on I, because you need a double derivative. If your double derivative is greater than 0 on I, it is concave up. If your double derivative is less than 0 on I, it is concave down. We can take the example of y is x cube. The first derivative will be 3x square and the second derivative will be 6x. Now, if we take any value to the right of the y-axis, that's your positive x-axis, you'll get your value of double dash, y double dash as a positive value, so you can say it's concave up. If you take any value to the left, so the negative x-axis, you'll get your value of y double dash as negative, so it's concave down. Over here, you will have the point of inflection as well. The point of inflection is defined as a point where the graph of function f of x has a tangent and the concavity changes. So for again y is x cube, your tangent is the x-axis at this point 0, 0, since the concavity is changing at 0, 0 origin. You see, this is the point of inflection because a tangent exists, and this is where concavity changes. Now you can even use the second derivative test to find your local extrema. It says that if your f double dash is continuous on an open interval containing x equals c, then if f dash of c is 0 and f double dash of c is less than 0, you'll get a local maximum. If f dash of c is 0 and f double dash of c is greater than 0, it's a local minimum. If f dash of c is 0 and f double dash of c is 0, your test is failing. So here f may have a local maxima or local minima, or either one of those two basically. We can take an example over here. Determine the open intervals on which the graph f of x equals 6x square plus 3 is concave up or concave down. So we have f of x equals 6 by x square plus 3 is continuous on the entire number line because it's a polynomial function. This I can write it as 6x square plus 3 to the power minus 1. I take it my first derivative and then using my uv rule. So u derivative v plus v derivative u, I get this value. For the second derivative, again I can take it up. I can take x square plus 3 to the up in the numerator, or I can just do the u by v rule, where it is v derivative u minus u derivative v upon v square, which on solving gives you this 36x square minus 1 by x square plus 3 the whole cube. So now by this second derivative test, you need to see what your value of f double dash of c is. So you take a region f double dash of c at 0. Now for this to be at 0, your 36x square minus 1 is 0. Basically your x square minus 1 has to be 0 for this f double dash of c to be 0. So you get x is plus minus 1. So now we are divided it into domains. Our domains are negative infinity to negative 1, negative 1 to 1 and 1 to infinity. Why do we take this f double dash of c equals 0? Because we need to test whether your concavity changes, and your concavity changes at the point of inflection which exists where f double dash of c is 0 or f double dash of c does not exist. So these are our domains: negative infinity to negative 1, negative 1 to 1 and 1 to infinity. Now over here your sign of f double dash, you can take any value between negative infinity to negative 1, any value between negative 1 to 1 and any value between 1 to infinity. Put it back over here in your f double dash equation down here and you solve it. For these values you get a positive, these values you get negative, these values you get positive. Since you have your sign of f double dash, you can determine the concavity, concave up, concave down, concave up. And now we know our function y is equal to f of x is this given in the question. we check at the point of inflection. So when x is 1, we put x is 1 over here, we get y is 3 by 2. We take when x is minus 1, y is 3 by 2. And when x is 0, y becomes 2. So we can then just make a rough sketch of the graph where we say, okay, over here on the left of the point, minus 1 is concave up. From here minus 1 starts becoming concave down, and then from 1 it starts becoming concave up. These are your points of inflections. The graph over here is a bit off, sorry, it should be at minus 1 and 1.5, it should be at this height somewhere over here between 1 and 2. Then you can say determine intervals on graph of f of x equals x square plus 1 by x square minus 4. Similarly, take the first derivative, take the second derivative, and then you need to see where your function is not defined or your function equals 0. Now if you can equate it to 0, you'll see your function will never be equal to 0 with the numerator. So then you check where it's not defined, which occurs at x is plus minus 2. So you have your domains negative infinity to negative 2, minus 2 to 2, and 2 to infinity. The sign of f double dash is positive, negative, positive. Concavity is up, down, up. At x is 0, y is minus 1 by 4, x is 2, y is infinity, x is minus 2, y is infinity. So in this case, your graph goes something like this. At 2 and minus 2, your y is reaching infinity. For x is 0, your y is minus 1 by 4, and over here, technically it should reach negative infinity.